Hello everyone, so I'll make 3 sets of videos talking about row reduction. In the first one I'll give a little context, background, and I'll talk about row operations. In the second video I will solve an example solution and I will perform row reduction on this example problem. In the third video I will talk about the types of solutions that you can get from solving or performing row reduction and what they mean geometrically. Row reduction is used to mimic algebraic expressions when solving a system. So what does it mean to solve a linear system? Well, it means you have to find its root. For example, if we consider this linear system here and we plot x plus y is equals to 1 and x minus y is equals to 1, we get an intersection, which in this case is 1, 0. So when we solve this linear equation, we are looking for its intersection point or its root. Since we have 2 variables here, the intersection is a point. But if we have 3 variables in the linear system, that could mean you have 2 planes that intersect at a line, or if they completely overlap, you have 2 planes that intersect in a plane, or 2 planes that do not intersect at all, in which case the root does not exist. But that's what it means to solve a linear system, is to find its roots. So let's consider this linear system here. The first step towards row reducing is to write this in augmented matrix form. In order to do that, you first have this box, and then you write each of the element into its corresponding cell. So here it'd be 3, 4, 4, 1, 6, 7, 8, 2, 9, 10, 11, 3. I like to draw this to separate the right-hand side from the left-hand side, but you don't really need to do it. So each column represents a variable. Here this would be x, y, and z, and this is the right-hand side. So the goal of row reducing is to have every element below the diagonal to be 0. So you can either get one of the 2 situation, whichever is your goal. One you can have in echelon form, where the diagonal components are 1, and everything below the diagonal is 0. It doesn't matter what the entries are above the diagonal. Doesn't matter. And another is a reduced echelon form, where all the entries are 1, and everything below the diagonal should be 0, and above the diagonal should be 0. There's one thing you need to look out for, is it goes from a column to column priority. So for example, if you have a matrix that looks like this, this is not in reduced echelon form, because the pivot position here should have been 1, and it's just below this diagonal. So you move like this. You move from the first diagonal position to the second diagonal position to the third, and that's how you prioritize it. Like, this position needs to be preserved if it can be preserved. In order to achieve this, we perform what we call row In order to achieve this, we perform what we call row operations. In row operations, you can do 4 things. 1, you can multiply any row. What I mean by row is this is row 1, this whole thing, this is row 2, and this is row 3. So I could multiply any row with a scalar factor. For example, I could do R1 substituted by R1 times 6. I could do R2 is equals to R2 times 4. I could do R3 is equals to R3 divided by 4. Or I could even do R2 is equals to R2 multiplied by a decimal number. Sorry, these should be cross. That's the first row operation that we could perform. Second thing you could do is you could add one row to another row. Or you could subtract one row from the other row. Third, you could add the scalar of one row to the other, or you could minus the scalar of another row to the other. Fourth, you could flip 2 rows. So I could just interchange this row to this row, and the new expression would have row 3 in place of row 2, and row 2 in place of row 3. So those would be flipped. Thank you for watching. Please like and subscribe my channel to support me. And if you want to watch the second part of the video, it's right here.